Hello everyone. In this video we're going to solve this year's Flare-on Challenge 5 from 0 to flag. Well, not exactly from 0. I will use some of my scripts and some ideas that I came up with while solving the challenge, but I will guide you through the entire process. What was my thought process while I was solving that one. It was a fun one, I can say. Um, the key to this challenge, I would say, is automation. Without automation, you basically cannot solve that one. Um, yeah, and I think it's a classic flare-on challenge that is not very hard to understand what you have to do, but you need the perfect tooling and the right methodology to solve it efficiently. So this is a re-upload. On 28th of October, I re-uploaded this video, Challenge 5, but I removed it because I noticed that after the half of the video, my microphone just died. Like the sound coming out of my microphone was so bad that I couldn't tolerate it at all, and I just removed it and thought that I can. I researched some stuff about microphone settings and stuff because, as you can see, this is a new one. Of course, I can use the microphone of my headset, but yeah, I was pretty hyped about the new microphone, so I decided to go with this one. And yeah, I added some filters and stuff. You don't care, but yeah, hopefully things are going to be better now. What else? So in this video, we're going to see challenge 5 itself. I think it will take some time, so I will let challenge 6 in a video on its own as well. And I think all the challenge from now on will be a single video, like challenge 6, a separate video, challenge 7, a separate one, etc. So without further ado, let's move on to challenge 5. The description is not that important, so we can ignore it. We know the zip password is Flare, so let's move on. Let's unzip. I have already downloaded the zip. Let's unzip it with the password Flare. Right? Okay, never mind. And yeah, first thing we do, yeah, let's change to list, not list, details. Yeah. First of all, a good practice to do when dealing with reverse engineering and malware in general. Okay, let's close this window. It's becoming annoying. A good practice is to rename exe files to basically nothing, because Windows work with file types. As you can see, if you add no file type to no file extension, sorry, to the file, Windows cannot recognize the file type. But if you add exe, then it gets this icon, which is a sign that this is an executable file. And this is dangerous because at some point, maybe you have maybe something's wrong with your mouse and you maybe double click it without you might accidentally click it, and you don't want it. You don't want this, especially when you do reverse engineering and malware analysis, because you might analyze some real malware out there. You don't want to accidentally click on it, double click on it. So yeah, it's a good practice to rename it. Yeah. So first thing we see is that the binary is quite large. It's 20 megabyte. So before doing anything, let's move on to the first analysis steps, the foothold steps as I say them. And yeah, import it into Detect It Easy. So first thing we see is that it's a C++ binary, pretty new, Visual Studio. 6 sections. Yeah, it's 64-bit. As we said, 19 megabytes. What else? Okay, maybe we should go see the visualization of it as we did in challenge 4. Um, while in challenge 4, um, the challenge 4 was large as well, but the big section there was the section, not which is not the same in this challenge. If I take out these all, you see that the text segment is what remains, and this is what takes up most of the space in this binary. This is pretty weird because if the text segment is that large, it's gonna be a bit painful for IDA to analyze it, to analyze the entire thing. So we'll maybe have some trouble over there, but anyway, it's good to know. Let's move on to the strings, I guess, of the binary. Yeah, just classic stuff. Let's scroll down a bit. Yeah, nothing interesting. Okay, and pretty early in the scroll list, one of the first thousands strings is not just one, basically. One of the first, um, some of the first strings in this list are these ones. As you can see, this is a YouTube link. We can copy it and go to YouTube and see what's that. And of course, yeah, it's the classic recall meme. This is a classic joke happening in CTFs, and when you see this link, it usually means that there's nothing to see here. This is just a troll, an Easter egg, like an Easter egg. So apart from that, we can see some other strings such as cmd.exe, the cake is a lie, some arguments for cmd.exe. This basically opens up a message box printing hello there hacker. You can see alert, no seriously, and yeah, in general there are thousands of them. Almost the entire data segment is filled with these strings. Yeah, until here. There are about 40,000 strings with these names. About 45,000, yeah. And the rest strings are just classic C++ stuff. So nothing to see here. This is all classic. Right? It's over. Yeah, okay. So before jumping into IDA and analyzing it statically, let's basically try to run it first and see what the binary does. Look, in most cases, let's change the, yeah. In most cases, if that was a real malware, I wouldn't go, I wouldn't prefer running it in my host machine. I would not prefer even running it at all, but never mind. Of course, I would use a virtual machine. We have discussed this in the previous videos as well, but this is a CTF. It's totally safe. The challenges in CTFs are usually not malware. If any binary messes up with your computer, you're most likely will be warned from the description of the challenge. In this case, there was no warning, so we assume that it's safe, and it is safe. So we can rename it to exe and basically run it from here. ntfsm. Okay, let's zoom this up. So the binary basically asks for a password, and it says that if there's some weird behavior with the binary, we can reset it with -r. So pretty quickly in the challenge, and we already know what's the purpose, what's the task of the challenge, and it is to find some password. Most likely the password will be either the flag or the actual password that will decrypt the flag, and we will get printed, and the flag will be outputted in the screen, on the screen. So let's go ahead and try submitting a password. And we get a message that the input should be 16 characters. So let's go ahead and enter 16 characters. And these are 9, 10, 1, 2, 3, 4, 5, 6. Yeah, if we add one more, 17, no, so 16, and let's go. Okay. I pretend that I didn't know what would happen. Okay, we can see that some message boxes were actually printed on our screen. You remember these strings cmd.exe that printed hello there hacker? Yeah. Some message boxes were printed on our screen, were popped up. So it's not necessary, but let's count them actually. So we waited for it to run, and we can see that after these message boxes, we get the message wrong in the end. Of course, this password is wrong, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And 1, 17, 16 or 17, anyway. So there was a message box. The number of the message boxes is the same as the number of the password bytes. This is pretty good to know from now without having analyzed anything yet. We will see that this is important for the rest of the challenge. So, yeah, I don't know what's left to do before going into static analysis. We can basically, yeah, I don't know. We could try some other passwords as well, but yeah, we already know what it does. Yeah, let's jump into the IDA. So let's rename it back, so we avoid troubles. And yeah, let's let it. Okay, let's let IDA analyze it. No, we don't want to connect to Microsoft Symbol Server. Jesus. Okay, it's pretty huge, so I will not let it analyze the entire thing because it will take centuries, and we don't want this right now. Okay. Okay. Did it crash? No, it did not. Thank God. Okay. We can see a lot of jump functions, and this I get some PTSD with that, to be honest. If anyone played the Flare on 2023, I believe. Yeah, it was 2023. The last challenge, Yoda, namely Yoda, had this pretty much the same pattern. Each function, there were a lot of functions having just one instruction and then a jump to the next function. So the pattern was function, one instruction, then jump to the next, then one instruction, jump to the next, one instruction, jump to the next, and so on. So pretty quick, we understand that there might be some obfuscation happening behind these jump functions. If nothing, if you don't determine it quickly that it's an obfuscation technique, then it's okay. You will understand in the future. We will talk about this. We will talk about this. So for now, let's stop the analysis and move on to the start method. Yeah, as I said, this is the start method. and it does nothing but just jumps to start. So this is the real start, and it calls just one function. This function calls two functions. The first one, you see that it's just another function doing nothing but jumps to the actual function, which is that. And the next function again, okay, this is not, it jumps immediately. But for example, take this now, and this function is just points to another function that does nothing but a jump, and the jump address actually jumps to the real function body. So this is a jump obfuscation technique. So in order to make the life of static reverse engineers harder, they have created a big jump table, a huge jump table, and so its function, you cannot see the function body directly. So you have to double click inside the function you want in order to see the function body. So for example, this, we want to see what this function does. Okay, yeah, we have to double click and go here and see what it does. Similar to this. I want to know what this does, but yeah, we have to double click and go here. Okay, and okay, what's that? Looks some shit with the security init cookie. Okay, never mind. We will get back to the obfuscation technique later. So let's go to the start again. So starting here, let's compile. Let's jump here, and we see that okay, this is pretty standard stuff. This is a security init cookie. This is some function that does some security init stuff, security init cookie stuff. So we just rename it and leave it as is. I suppose the meat of the program will be in this function. So moving here, we see a lot of functions and a lot of these annoying calls that the annoying jump calls that I told you about earlier. Yeah. Let's navigate pretty quick to each of these functions. Yeah, we don't see anything particularly interesting. Okay, why crashed? Oh, okay. Okay, so we were in this function, right? We go here. So I have solved the challenge, so I know that this function cannot be compiled at all with IDA. But let's see why. Let's go back to the assembly and jump to this function. If you see, the stack of this function is already large and it's not even disassembled properly. If we disassembled all this code, the stack would be much larger. So for now, let's go to Control Alt D, I think. No, Control D. No. Let's go back to it. So, okay, let's press Alt P and see some info about this function. And we can see its size. It's pretty big. Basically, you can find out with this abstraction that the size of this function is basically 13 megabytes. It's an enormous function. Like almost the entire binary is only this function. It's filled with this function. It's enormous. And if we go to the function list and if we go to the function list and sort the functions by length, we see that the last one, it's the C0B0 with this size. It's enormous. And the rest functions are very, very much smaller. So we assume that, okay, this function has some interesting shit inside. So let's generate the string of the list of strings. We can do so with Shift F12. it generates the list of strings immediately. Okay, we'll wait a bit. Okay, these are the strings that we saw earlier in the detect easy. So let's close it. Yeah. So let's jump to these strings. We see that these strings, we have not analyzed the entire binary, but so these strings do not have a direct reference yet, but some of them do. And for example, this string cmd.exe is referenced by this big function that we saw earlier. So, okay, we're pretty sure now that this function has some interesting shit that we care about. Let's go ahead and rename this function to gigantic function. Yeah, these are the names from the previous video that I recorded yesterday. Yeah. So this is the gigantic function. We we're in the beginning of this function and we immediately see some promising strings like state input. This is probably our password, has something to do with our password. This is the position and the transitions. We don't know what these are, but we see some more interesting strings here. This is the correct message. This is probably printed when we enter the correct password, I assume, right? This is okay. If we scroll down a bit, we see the wrong message. This is what was printed to us here. So this message is printed when we enter the wrong password, apparently. And yeah, so if it jumps here, then it's the wrong area, right? And most probably this function is the print message. So it prints wrong, right? It loads the string to the RCX, which means it's the first argument of the function. Right? The calling convention says that RCX throws the first argument, RDX the second, R8 the third, R9 the fourth, and the rest are stored in the stack. So, wrong is printed, and eventually, what's that? Okay. Okay, so let me check. So the first argument is 1. It's passed. Okay, this is the argument. RSP plus 8. Oh, it adds 28. So 28 plus 8, 30. So, okay, so this is the first argument. It's loaded again into RCX. So, sorry. A1 here is the value 1. It's printed here. And, okay, so this function basically calls exit process. So it makes sense in a way that it prints wrong and it just exits, right? As you see. So this is a wrapper of the exit function. Okay, interesting. Moving along, we see that this is the message being printed when the password that we enter is not precisely 16 bytes. So this check basically most probably checks the number of arguments. So this is argc. So okay, real stuff. So if the number of arguments is 2, it jumps to the real, let's call it actual main. Yeah. So in the case that the number of arguments is not 2, exactly 2, it prints that the usage is this and it exits. It exits again. So our renaming was correct. Yeah, so Let's jump to the actual main. And here it exits with 2. Why? Wait, what? Um, what the fuck is going on? Anyway, okay, this is probably not the actual main. This is something else because it exits. What the fuck? Anyway, oh, oh, okay. So it jumps here. Okay. Where? Oh, okay. So, here is the string that was printed when we entered the password that is not precisely 16 characters. Yeah. So there was one check for the number of arguments, and now is the check for the number of the password characters. Okay. So here it checks the RAX that whether it's 16. This value is 16 in decimal. So this is probably str length. It computes the length of the first argument. So this is our password. Right? Cool. This has to be our password. So what? Okay. No. Okay. So if the length is not 16, it exits again. Otherwise, it moves to the. Okay, this looks okay. Okay, so this is the actual main. Actual main. So you might be wondering, why do I not try and decompile this function? If you solve the challenge, you probably already tried that. If you haven't solved the challenge, go ahead and try decompiling it. Your IDA client will just crash. And yeah, I think I'm pretty sure that at least in IDA, I've heard some good stuff happening in Binja, but at least in IDA, you have almost no chance. You have zero chances of getting a good looking decompilation for this gigantic function. It's literally enormous. It's like 13 megabyte. Uh yeah, it's probably not doable. So this is the actual main though. Scrolling a bit, we can see a, a jump table, a big jump table with 65,000 cases. Okay, if we jump to the jump table, we can see these cases. Yeah, there are too many of them. So okay. Oh, and here are the strings and the message boxes that we saw earlier. So scrolling a bit, we see a message box being printed. Some message boxes with these messages. We appreciate your efforts, but due to some other stuff. The presence is another castle. Some various strings. We don't know what they are. Yeah, and we see shell execute A. It opens the CMD and and pops up a message box with this message. Hello there, hacker. This is what happened in our case. So it turns out that there are much more. There are many more Windows API functions being called. For example, sleep with just a huge number. I think this is 500 seconds or something like that, or 50 seconds. I don't know, but yeah. Um, Looking at the spoiler alert, one of these cases calls a specific Windows API and just signs us out of our Windows system. Um, yeah, this is a pretty good indication that getting at this specific, for example, if we get into this specific state, then this probably means that our password is wrong, because I don't think the intended solution would be to wait 500 seconds to get the password, to get the flag. So getting to this branch probably means that you fucked up somewhere, right? So yeah, we have to start the analysis from the beginning of this gigantic function. Okay, so going back to the beginning of the function, we see the strings being loaded here. Um, we see this function being called multiple times. So we assume that this does some init stuff. Moment. Oh, I want have- okay. Okay, so we don't know what this does precisely, but it does some init stuff. Okay. This print's correct. So let's analyze what do we need to do to get actually the correct message. So we need this variable to be 16 and this variable to be 16. Remember that the length of the password is 16 as well. So what's that? So first of all, this function is called and the string state is passed as the second argument. The first argument stores this variable. So we assume that this is some state var. Yeah. This is some input var. This is the position var. Transitions var. Right? And it probably does some initialization things in here. So this is probably some check that has to do with the length of the password. So some kind of check happens 16 times, one per password, or one per password character probably. And if everything is okay, we get the correct message. Yeah. So if this variable is 16 and this variable is not 16, then we get wrong. So second value, no, I have already renamed this, it's not my fault. So this is the first value that needs to be 16 and this is the second value to be 16. This is our targets. This is our target variables that have to be 16 in order to get correct printed. So if this is 16 and this is not, then we jump to the wrong area. If this is not 16, it just moves, it just runs the program normally, right? So we need to start from somewhere. We need to see actually how our password bytes are checked. How is our password processed in this binary? We know that it must be of length 16. It contains ASCII characters, okay, but we don't know how the password is actually checked. So how can we proceed now? First of all, something that I did in the challenge before moving on with analyzing this function, I decided that I thought that I was too annoyed having to jump to each of these functions one by one and double click to see the actual function body. So having solved Yoda from 2023 Flareon, I decided to write a quick deobfuscator, a quick jump deobfuscator for this particular obfuscation technique. And this obfuscator is basically inspired by my tool that I made back in Flare 2023. This is my tool basically. And what it does is the challenge was like this. So the obfuscation there looked like that. There was an instruction, then a jump, instruction jump, instruction jump, instruction jump. You can see that you can see the similarities. In both cases, to see the actual function body, the efficient instructions actually doing something, you have to double click and double click and double click all the time. So I wrote a deobfuscator that does what basically? It runs over this function and follows the jump chain and basically tracking all the instructions and dumping all by all in one. So for example, deobfuscating this is equivalent to this code. In the end, I got some pretty satisfying results. Not 100% deobfuscated, but I was satisfied. So yeah, I based my entire solver on my entire deobfuscator for this challenge, the fifth one, from this. This is pretty much more complex, so we will not dive into it. I have a documentation and some comments. I think you will find your way there. So let's go ahead and see my deobfuscator for this challenge specifically. Jump deobfuscation. Yeah, this is my cheat. So jump deobfuscation. Let's see. So this code basically supports three methods for the time being. First, we are able to basically run the deobfuscator to all the callee functions. A callee function is a function that is being called somewhere in the program. So this is our first option. Our second option is to deobfuscate the entry point only. So remove all the jump from the functions that exist in the entry point. I don't like the brightness here. Okay, it's fine. And the third option is that we can deobfuscate a specific function. For now, and because as you can see, the binary is pretty large and we don't want to wait, we will try deobfuscating just this, because this is the function that we will spend most time analyzing. So we change the selected method to 3. OEP is ignored basically, and the specific function that we want to analyze is this one, C0B0. So we set it here. It jumps to deobfuscate this one. So how does the deobfuscate work? First of all, let's print the opcodes for each line. So let's rename this back. So because we care about this specific address. So how does the deobfuscator work? It basically runs through each instruction of the method, and for each call that calls to another function like that, we don't want indirect calls. An indirect call is, for example, call RAX. We don't want this because we don't know what's the value of RAX at the runtime, and our purpose is not to evaluate the value of RAX at the runtime. Our purpose is to just have a more convenient disassembly. So click here and just get immediately here. Our purpose is to click here and see this directly. So basically ignore this function entirely. So how does this work? It checks the callee address, which is this one, and gets here. It checks, is this function inside the range of functions inside of the functions? No, how can I explain? is this function in the range of the jump functions? Because as you can see, and as we saw earlier, that these jump functions are all defined consecutively like that. So this is a range, right? So this range starts from the beginning of the text segment. So basically from the very start and goes until, yeah, I will probably have to scroll for quite a while. Let's zoom a bit. Yeah, this is so bad. Yeah, this is probably it. I don't know why I do this right now. Never mind. Okay, here it is. Okay, nice. So the range starts from the very beginning of the text segment and ends here. So this is the range. And we check, is the function that we call now in this range? If it is, then go into the jump address, follow the chain of jumps until we land to a place that it's not inside this range. So this function does not belong to this range. As you can see from the addresses, it's very far ahead from the range. So, okay, we found this function. What do we want to do? We want to replace this, and instead here it should say that. So instead of clicking here and jumping to here, we want to click here and jump immediately here. That's a logic. But before getting into it, how do these call instructions work in assembly level? So as you can see the opcodes, the classic opcode for a call instruction is usually an E8 opcode or E9, usually E8. Okay. So E8 is fine, but what about these 4 bytes that are that appear afterwards? So these bytes are basically the relative offset of the function being called. So what does it mean? It calculates. So let's take, for example, this function. This is let's start that. Suppose this is the target. Okay, what's the beginning of this? This is start. For example, it's that one. Let's print start. Let's print target. So look at this. It's this number is basically a 4-byte number represented in little endian form. Little endian. So it's written backwards. This is basically 0x ff 68 638. Okay, but so this is basically the relative offset. This offset is calculated by subtracting target from start, then removing 5 more. You can see that this number is negative. This is fine because this number, as you can see, starts with an FF. This means that these numbers are signed numbers. So this is a signed 4-byte number in little endian. Signed means that when the number is negative, it basically starts with FF, all ones. So in order to see, to convert this to hex, we basically reduce this number mod 2 to the power of 32. This is a 4-byte number. 32 is basically 4 multiplied by 8, so 4 bytes. So calculating that and hexing this out, we get the exact same number that is here. So this is how the relative offsets are calculated. And it's pretty interesting because we know This is pretty interesting because we know what's our real target now. Our target is basically this function, right? So our target is that. Let's recalculate this number, and it's that in this case. You can see that this number misses the first byte, which means that it's just zeros, which means that this number is positive. It's a positive signed number. The previous one was a negative one. So the goal is to replace this number. So we have to replace this with basically this. So we need to represent this number in little endian, starting from the last byte all to the start, and going to the start. So 1356 FE00. So this is basically what my script does in automatically, of course. So it gets the current mnemonic. As I told you, it analyzes its instruction. So it gets the current mnemonic. If the mnemonic is one of the returns, it means that the function is over. So we basically break. The iteration finished and we jump out of the loop. In other case, we calculate the instruction size. So we get the instruction size using using the IDA Python API, which is decode instruction, and we get the size. So we basically get 5 for this specific instruction, then 4, then this returns 1, this returns 5, etc. And we get the size. And we check, is the current mnemonic a call instruction? Because as we said, we track only the call instructions. If it's a call, and if the size is 5, why do we check this? As I said earlier, we don't want the call RAX calls. This is an indirect call. Let's see something. If you attempt to assemble this instruction, not 86x64, you can see that an indirect call is basically 2 bytes long. So checking that the call instruction is 5 bytes basically ensures that it's a direct call. So a call to a function, a real function, right? So if that's the case, we process the call and we get the target function. In our case, the target function for this example is this. We will see later how this is calculated, but take this for granted right now. Trust me, bro. So we have this check as well. We want to make sure that the target is different than this, right? So yeah, in that case, we calculate the new address. So if they are signed integers, so in case the number is negative, we module out, we do a modulo operation with 2 to the power of 32, exactly as we did here. It was negative, so we had to reduce mod 2 to the power of 32. Okay, I will change the light right now. I think it's a bit better right now. Yeah. Let me check something. Okay. Never mind. So if the number is negative, we reduce mod 2 to the power of 32. And we pack the number as a 4-byte little endian integer in signed form. This is the way to do with the struct module. It's a pretty useful module. You can just do all of this, represent as signed, not signed, represent as 4-byte little endian using this string. Okay, and we actually patch those bytes. We actually patch those 4 bytes starting from the current opcode +1. So we patch those 4 bytes with the target, the relative offset of the target function, which, for example, in this case is that. So let's go ahead and basically run the script. Oh yeah, the process call. How the process call works. As I said, um, it jumps into this function. It checks if it's inside this range. So I have noted down the range of these jump functions. As I said, it starts from the very beginning of the text segment and ends here. If I jump to this function, you will see that this is the end of the jump function range. Right. So while the jump addresses are fall inside this range, we just keep following the jumps. We keep following the jump chain until we land to an address that is outside of this range. Then we mean that we found the actual function body. And we return this function address. So yeah, this is pretty much it. The logic is it's not very complicated. So let's go ahead and run the script. Nope. 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 Um, this was it. Yeah. So it will take some time, but yeah, you can see that pretty quickly it will patch this out. Wait. Oh fuck! I didn't save that. Shit. Yeah. Let me save it. Why did I not save it? This is hasdb lol. Okay. Kudos to Hercore for this project. Um, yeah, so we're going to replace 3. Okay, now it will work. So let's run this again. You will see this being patched pretty quickly. See? It found the target address and it patched it out. So we'll wait for a quite while. It's not much, but it's some honest work. You can skip this part if you want. My PC is on fire. Hmm. Okay. It's a pretty large function over here. Okay, it finished. So now you can see that we can directly jump to the function body and we're good to go. For example, this now you see that we can directly jump to the function body, and yeah, this function was not deobfuscated, so we have to jump again, but it's okay. Yeah. So back on renaming stuff, let's rename it this to does some init stuff. Okay. So this is the position. Um, we assume that the input var is the variable that has to do about our password, probably. But what exactly are these strings? What are they variables? What are they exactly? We don't know yet. Um, so let's navigate a bit into these functions. Yeah. Okay, pretty quickly, we see this create file, read file, which look promising. Um, so this create file basically reads from what file? Wait, this method, what does this return? It returns, what does it return? V7? What's V7? Oh, okay. V7 is a module to the current file that we're analyzing right now, NTFSM. So it basically opens a handle to the current file. Um, okay, you can search this in the Windows API docs, but this is open existing. This is file attribute normal. You can check this out from here as well. So 1, 2, 3, 4, 5 disposition. You can see that number 3 is open existing, and 0x80 is file attribute normal. So what does open existing do precisely? Only if it exists. Okay. So it opens the file. So if the file exists already, then it reads from it 8 bytes long. Okay. And it closes the handle. It closes the handle. But yeah, does this mean that it reads the first 8 bytes? What 8 bytes? Like, it does not make sense. We don't know what bytes exactly are read here, but never mind. We will get back to this a bit later. So, moving along, yeah, let's go, for example, to the wrong area. It prints wrong, and again loads this transition state stuff. So this might be does some cleanup stuff. Don't know, and it exits. So why did this not exit? Oh shit, yeah. This was exit wrapper. Yeah, I shouldn't name this. This is a jump. We want this to be the exit wrapper. Okay, cool. So yeah, we basically navigate through. Oh, what the fuck? We see some CBC stuff, AES. There is some AES here. Oh, so when correct message is printed, then we get into this function that has some big crypt stuff, some CBC. Let's decompile it. Okay, we see that this is some cryptography related stuff. Oh, and we see the string your reward. Okay, so this probably is the flag. So if we enter the correct flag, we probably get inside this function. And okay, there is this array that's probably the encrypted flag. And yeah, basically the flag is most likely decrypted with the password. And most likely the password is hashed with SHA-256 and is then used to decrypt with ISCBC, and the key length is 32 bytes. Yeah, so we can most likely assume that the 32-byte key, is the hash of the password. Okay, so it's good to know that this is basically decrypt flag, decrypt and print flag. So yeah, no, we don't want this. We want to name this function directly. Okay, cool. So this is fine. This is good now. So um, why not go ahead and debug this a bit? And we want to breakpoint to create file and see what file is actually opened and what bytes are read from inside. So let's open this up. Let's provide the password. Shit. Okay. So let's refresh. I think the password is saved. Yeah. So let's breakpoint to create file A and read file. Cool. Let's run it. Okay. As you can see, it reads the oh, it reads the binary NTFSM, but with a colon and then a state. So we're not pretty okay. Where is this file? Where is the colon state file? Never mind. It then reads some bytes from this file. Then it calls that again with the colon position. Okay. Then colon position again. Then transitions state input. Okay. So what are all these files with a colon inside? Where are they? Are they invisible or what? Let's research about this. Um, um, secret NTFS secret files colon. Okay, you can see that we get some pretty interesting results. Alternate data streams, and this is the pretty much the same pattern. This is a file name colon some other name. Okay, so it prints, it lists the files inside this directory. You can see only text.txt. However, um, we can see that there is an additional ADS, an alternate data stream inside, named secret. Oh, that's nice. And we can print actually all the hidden secret, all the hidden ADS with the /r option. So why not go ahead and do this actually? So, and voila, we find out that there are 4 hidden alternate data streams for this specific file name. Um, so yeah, this is pretty interesting. So yeah, 4 different ADS associated with this file name. So this is pretty good to know. Um, basically, you can research this, but trust me, bro, for this one, alternate data streams are basically it's a way in this challenge to store information in a secret way that you cannot just see with a dir instruction. So it basically stores this kind of information. This, for example, input is 16, which probably means that this is our password. And in fact, if we run this command, colon input, and write the result, so if we run this, we see nothing. But if we write this to out.bin, then out.bin is filled with something, and more specifically, basically empty. It's empty. This is probably because these streams are not written yet at all. So the important thing is that it's a way to storage information inside. in a secret way somehow, hidden in plain sight, basically. So this function that we saw earlier, what was that? This one. Yeah, this pretty much creates a handle to this hidden ADS and reads the 8 bytes from it. So basically, where is it? Oh, yeah. So this is create file. So ADS read. Let's call it ADS read. It reads, no, ADS read 8, basically. Okay? Read 8 bytes. Now we're fine. So this read 8 bytes, this reads 8 bytes from the ADS. What ADS? Okay, so the transitions ADS is the second argument to this function, does something, blah, 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 then reads 8 bytes and stores them potentially here. Yeah, it reads 8 bytes from the transitions and stores them to this variable. So this has to be the current transition number. Not the current, sorry. Is this the current one? Yeah, I guess it loads it. And yeah, so there is a similar pattern over here. It reads the position ADS and it reads 8 bytes and reads the result here. So this should be current position number. I have already renamed. So this most potentially is not the cleanup stuff, it's just some ADS load or some ADS reset, I don't know. Probably ADS load. Opening this up, we don't see anything particularly interesting out of the blue. Yeah, we have to dig a lot and this is annoying. Yeah. It's not worth. We can just understand from the context what this does. This most potentially loads the position. Sorry, it stores the position. It reads the position. It loads the position ADS and reads 8 bytes from it. Okay. So this is so this should be ADS init, and we have renamed. We have already renamed a pretty good part of this function. We're very far away from understanding what this function does, but we're getting somewhere. Okay. So this should be print message. Oh shit, I renamed the other one as print message, right? Yeah. Yeah, we don't want this. This is print message actually. The other one was print message obfuscated. Right? So this is ADS init. Okay. What's that? Read file again. So oh, yeah, this is not deobfuscated, so this is annoying. Never mind. This is JS load, ADS load. So this creates again a handle, but now it does not read 8 bytes. It reads as many bytes as specified in the third parameter. So that would be R8, and this is the third argument, as we said. Where is it called? Where is this called? It's called here. No, no decompilation. No. No. Fuck, I need to close this. Sorry about that. Okay, so where is this function fucking called? This is called here. And this is called here. Okay, so in that case, the third argument is 16. So as you can see, yeah, it matches our renamed variables. It loads the input ADS, which is 16 bytes long, and basically reads 16 bytes. So this is ADS read. Let's call it n bytes because it's a variable number. So it reads the input, it reads the entire input, and you can see where it goes. It reads the entire password and uses it to decrypt the flag. So moving along to our program. So we don't care about this branch, or we want to go to the actual main. Okay, so what's that? Oh, as you can see, this method is of similar form. It opens the handle to the ADS, but now it writes to it. So this is most likely, this is ADS write 8 bytes. No, write n bytes. In this case, it writes 16 bytes. So it writes, this is where actually our password is written in the ADS. So let's put a breakpoint here actually. Right? No, what the fuck? Oh, yeah. So you can see this is our password. So running this again and dumping the input ADS to out.bin, we can now go ahead and see out.bin. And as you can see, we can see our input having been written inside. So our educated guesses were correct. This writes n bytes to the specified ADS. So now this is an equivalent function, but it writes 8 bytes exactly. So we can rename it to ADS write 8 bytes. Pretty simple. So this writes to the position the position ADS, and this writes to the transition ADS, and this to the state. We'll still have to analyze what is this position, transition, and state. We can assume that position ADS is just the current password byte being checked. So the first time is 0, the second time is 1, third time is 2, etc. So this is position, and let's break point here. We can see that it writes 8 bytes to it. So let's go ahead and dump the position ADS to the same binary. Okay, nothing interesting. It's just empty, so it's probably null, 0. Same with transitions. The value 0 is written. Same with state. The value 0 is written. And now, as you can see, it opens the input ADS and it reads 16 bytes from it. Thank God. I had put a breakpoint from since yesterday here. We will analyze it later. So it read 16 bytes of input. Okay. So okay, the 16 bytes of the input were actually read here. So as you can see, it reads the input and so let's see. Okay, so it reads that many bytes and stores them to the second argument. So the second argument contains these 16 bytes. So what's the second argument? This is the second argument. So this is the password actually. I think I have already renamed. Yeah, there is already a password. Fuck. Okay, let's rename this back to rgate and yeah, use that as the password. So as you can see, it loads the 16 bytes of the password, stores them here, and loads the password to the RCX and moves exactly. So this is the current position and moves the pointer of the password by as many bytes as the position indicates. Um, in the first position is 0, so it starts at the beginning of the password. Then potentially we assume that position increases by 1, so it jumps to the second password, to the second byte, then to the third, then to the fourth, until it reaches the entire thing. So this adds the password by 1 or by 0 in the beginning to begin with, and it dereferences the password and stores the byte here. So this is the current password car, right? Um, nice. So this is the current password car, right? Okay. Then it initializes some other stuff. I don't know what this is. Compares this keyword. Um, yeah, it jumps here and it compares rax with this constant. So we will get back to this in a while. Let's see first what is this jump RCX thing. You can see that there is an automatic comment having been made from IDA that says switch jump. So a jump table in assembly level is basically a switch case in our high level languages like C, like C++. So if we write a switch case behind the scenes, the compiler and in assembly level, this will be represented as a jump table. So in this case, the switch case is pretty large. It's 65. IDA says that it has 65,000 cases. However, before jumping to the actual case, there is another check that checks. So this is basically current case num. Yeah, I have already made these names. So it checks if the current case is greater or equal than 90,780. If that's the case, then it jumps to something wrong. So something went wrong area. So this is a hint that usually in switch cases, as you know, what was that? Okay. As you can see, usually in switch cases, there are the normal cases that we know, case 789, and there is a default. So this is the case that is entered when that none of these cases match the value of num. In our case, the default statement, the default case, is the one that is above 90,780. So in our case, this switch case has 90,780 cases, and the default one jumps to something went wrong. So this means that the cases are, in reality, there are 90,780 cases and not just 65,000 of them. This is how switch cases work in assembly level. So we certainly know that there are that many cases. there are a lot. These are a lot of them. No wonder that this function cannot be decompiled at all. Yeah. So um, yeah, this is classic stuff. If maybe there are some information here. Assembly jump table switch case. Maybe there is some stuff. Mm, no, like that. Yeah, this is pretty close to what actually happens. So as you can see, it jumps to, it has an indirect jump here to a register. So this, so here is the actual jump to the corresponding case happens. Um, we don't know what variable is exactly here. So in the previous case there was num. We don't know what's the condition that determines the current case that will be entered, but we will see it in a while. If we scroll down a bit, we can see the case 46,369. This is the entire case. It ends here. Then the next case starts. And as you can see, there is pretty much a pattern. Like all of these branches start with the RDTSC instruction and end with a jump back to when, to where? Yeah, it jumps. This jumps here, and this jumps to it jumps to the end of the function. So this basically, yeah, wow. So this is basically jump to exit area. No, jump to end area. This is more suitable. So um yeah, you can see this pattern. Most of these blocks start with RDTSC and end with a jump less. This pattern is very common everywhere. You can see this happening. If we scroll down and jump to a random case, then you will see this exact same pattern again. So this is pretty interesting. So what is the RDTSC mnemonic exactly? Okay, this is some Greek description. Okay, so RDTSC reads the timestamp counter. Mhm. And load some things in EDX and EAX. Okay, you either know it already or you don't, but I think that this is pretty much an added debugging technique, if I understand correctly. Otherwise, it's just garbage. If you research here, timing added debug, so this is a common way to determine whether the current application is being debugged. So it calls RDTSC once, so it loads the current time, then does some stuff, then loads RDTSC again and monitors the current time, and subtracts the end from the start from the end time. And for example, if this is greater than a specific value, then this means that okay, this application is being debugged. This is a not so efficient debug technique, but it used to be to exist and be used a lot in malware and stuff. Anyway, as you can see, um, yeah, sorry, okay. As you can see, this function pretty much has nothing to do with the rest of the body because the main body of the case looks like it's this, like you can see that. Okay, let's change this. Okay, so as you can see, these variables are used nowhere inside this important logic of the actual case body. So we can potentially just ignore this for now and focus on that. So let's go back to the first case. How can we? Mhm. Okay, so not the right area. No, 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 no. Where is jump RCX? Here it is. So for example, take this case. Inside the first case, so we can see that the current password character that was dereferenced up here is accessed. But then it just prints the message sandbox is here, this one weird trick, and it prints it with a message box. This is an indication, as we said, that most likely any Windows API call here is an indication that most likely the password is wrong. Because if that's the case, then okay, there are 90,000 different API calls. Do we need to find the correct order of these API calls? For example, do we need to run sleep for 500 seconds, then message box, then print this message, then then print this hello hacker? What would be the right order? This is a strong indication that if we get here to this branch, if we reach this branch, it probably means that the password is wrong. So, okay, let's skip this case for now. Let's move to the next one. 41,257. So, let's again ignore this block and go directly to this block. So again, the current password character is checked, is loaded into EAX. The last byte is used only. It's loaded in this variable, and this byte is checked if it is equal to e, lowercase e, or lowercase x. So, okay, we have a direct check with the actual password character. So it checks if it's e or x, but it's the case 41,257. What password character exactly is checked here? Is it the first one? Is it the second one? The third one? Which one is checked for against these numbers? We don't know. So suppose that this specific character is E. Then it jumps to this particular branch. And it updates this variable with this value. And if it's an X, it updates with this value. In any case, if it jumps here, if it jumps to this branch or this branch, you can see that the message box is actually skipped. We skip the message box. That's a good thing. You can see that if it's neither an E or an X, we jump to the message box, which is an indication that assume that the program at some point reaches to this specific case. Then we want either this password character to be an E or an X. In any other case, a message box is popped up, which means that the password is wrong. Okay. So, yeah, we're not okay. First of all, what is this number? This looks like an index inside this huge switch case. So it looks like, let's basically debug this. We don't have any other clues right here. Yeah. Where is the yeah, let's jump to the jump RCX. Let's try to understand, first of all, before jumping in, let's try to understand how is actually the current case that is being entered determined. So how does the program determines in which case it will jump now? So the jump table is loaded into the ECX. Okay, Rax has the base image address. So current case num. So current case num is used to as the offset in this huge jump table. Current case num. And current case num is rax, rax, and rax is this value. Where is this value written? Oh, this is interesting. Why J? Why? Why that? Why? No, this is not correct. This is not correct. Ah, this is not correct. Ah, is it? It's probably. Never mind. Never mind. So this is the basically the current case num, right? So um, some bytes are read from what though? What's the okay? Some bytes are read from a specific ADS, and these bytes are stored inside this variable. So, how, however, what ADS is read? We can see the load that loads in the second argument. It loads the state ADS. So this is the state ADS, and that's a good thing, right? So this is the position ADS. It's a good thing. Okay, so if you didn't understand yet, we figured out what is the state ADS. The state ADS is basically the index, stores basically the offset, the index of the next case of the jump table. So initially, this state is 0, is set to 0, right? You can see that initially, yeah, it's checked among -1, but never mind. Initially, this is 0. Okay. Okay. So, um, from this, we can understand that the state ADS is the most one of the most crucial ADSs because it determines the next case that we will jump to. So, for example, in our case, state is initially 0, so it jumps to this block. If I press Alt Insert and jump to this block, of course, it's not decompiled or disassembled. But yeah, let's disassemble some of it. Okay. So let's go back again. Alt and Insert from inside x64dbg, and we jump to the case 0. Okay, so this is pretty interesting. This means that the first time the state is 0, as we said, and it basically jumps to the corresponding block. which is case 0. What else? So let's debug this a bit. We can see that this code is pretty useless. It literally did nothing, just did some timing stuff and then just moved out of the loop, never jumped back. So we don't give a fuck about this. So the input is loaded into AX, the first byte, 0. If you remember, I gave it that password, so first byte is 0. So it's loaded here, and it's compared among J, U, and I. And as you can see, it matches none of these characters, and it jumps to cell execute. So we get this message box. And this means that this is the wrong password. Now it jumps here and check this out. It loads the position, ADS, and check this out. It writes the value 1 to it. So it increases the position by 1. You can see here, it loaded the position, increased it by 1, and eventually, yeah, it stored RAX to DC0. Then DC0 is the second argument, so 1. So yeah, the position is increased by 1. Okay, we don't want the breakpoint anymore. So never mind. Okay, we don't want write file as well. Yeah, let's close this up and move along. So here the transition is loaded and 0 is written, nothing changed. Remember that. Let's go back to the correct message basically. So where was that? Yeah, correct. Correct was loaded here. So remember that when the current position is 16, we also want the transition to be 16. So in our case, the transition did not increase. In the case of the correct password, this should be increased. So for example, here you can see that jumping to any of these cases, either to the case J or to the case U or to the case I, any of them, the transition is actually increased. So this is a good sign. In our case, we jumped here, which means that bad news. Transition is not increased, so we have no chance of getting this value to up to 16. So let's move along. There are some other functions here. What does this function do? We're not sure yet. Oh, that's very interesting. This function calls create process. So what does it do? You remember that 16 different we were printed 16 different message boxes were popped up. Yeah, this call of create process shows that it runs the same binary again. So it spawns the child process inside the current process and runs the password check again with the new data. So it runs again the password check with the new value position, the new value of transitions, and the new state. So it basically runs itself again. If we go one step before, you can see that the process that is being spawned, it's literally the same binary. If I run this now, it will print 15 times the same message box. So I prefer to ignore it for the time being. So yeah, let's go back to the case 0. What was the case 0? This was the case 0. So in order to understand how it exactly works, yeah, we need the variable names, man. Do you know that? Okay, so this is the current state. Okay, let's for example jump to, suppose we enter first byte as U. So the first byte is U. We refresh, and wait, let me check. What's the value of the state right now? We want it to be 0, right? Okay, it's 0. So, Jesus. Sorry. Something. Okay. So, we are in case 0 again. First byte is U. So, we are supposed to jump here. Nice. Okay, now what happened? I know what happened. Do you remember the message that we saw earlier that it said in order to, in case of any weird behavior, you can reset the binary? This is an example of a weird behavior. And what happened basically is that the old input is still in here. Our new input is not actually written in the IDS. So what I did during the CTF was create a PowerShell script, reset.ps1, and let me show you what it does. This basically, yeah, let me delete this. So what I basically do here is that I just delete entirely the ADS streams. So I reset them so they're clear and they're created from the begin, from scratch. So let's run this PowerShell script. So you can see the ADS now, and now you can't. They're gone. And if we refresh the debugger and write the input to out.bin, you see that the updated value is written. Okay, so we jump to the first case. Okay, garbage, and now I should jump here. Awesome. So the current state is updated, and also the transitions is updated. As you can see, the transition is increased by 1, which is something that we want. We want it to hit 16 eventually. So it updates the current state and the transition. Very good. So we jump to the end. As you can see, it writes the new value of position. It wrote the value 1, and the new value of transitions, which is also 1. Great. Let me rename this pretty quick. This is the create process wrapper. So, okay, we don't want to spawn the new one. So, let's go ahead and see what's the value of state now. Okay, the value 3 is not written yet. Some weird shit. Okay. Oh yeah. Okay, state is gonna be written now. So you see that the value 3 is going to be written to the state ADS. Okay, it run. Let's dump the state. And we see the value 3. So now we don't want to go to spawn an next process, so we just refresh it. And now check this out. I'm back on the beginning of the switch case. If I click and F7, then and click Alt Insert and jump to this address, we can see that we are inside case 3. So our educated guess was correct. The current state determines the next case of the switch case, of the switch, yeah, the case number inside this switch case. So now the second, presumably the second character is checked. So it loads, yeah, it loads the second character. So 1, and it checks, is it P, is it Z? In our case, it's nothing. So look at this. Oh yeah. Oh shit. This is actually fun. Okay, in this case, exit Windows. I did the mistake to run this accidentally during the contest, and I just got logged out of the system. So check this out. It logs off the interactive user, shuts down the system, or shuts down and restarts the system. This sucks, believe me. So the value 4 is passed, and value 4 is flag has no effect. The system. Yeah, apparently this just signs you out and does not give a fuck. Oh yeah, and ECX is 0, and 0 means log off. So yeah, if I press F8 now, my Windows will be logged off. I don't want this. So let me close this. So what do we know so far? We need to somehow represent this problem. We need a way to represent. So starting from state 0, we can go to 3 different other cases, which are case 1, case 2, and case 3. So from case 0, we can go to case 1, case 2, and case 3. So we know that if we enter J, we can go to switch to case 1. If we enter U, we enter case 2. If we enter I, we enter case 3. Now, 1, let's go to the jump table. How? Okay, perfect. So, this is the first case, this is the second case. Let's pretty quick. Okay, great. So where is the case 1? Please. Yeah, case 1. This is the case 1. So from case 1, we go to case 4 and 5. From which characters? We go to case 4 from character L. And we go to case 5 with character Q. You see where it goes? We need to do this for all the cases up to 90,780. And yeah, this is pretty much the solution of the challenge. So, how are we going to deal with this? We need automation. That's why I told you that we need automation in this challenge. Otherwise, it's literally impossible to do by hand. We need somehow to figure out a way for each case to know what's the potential next case and which character leads to that case. In the case of 0, all the potential next cases are 1 to 3, and these are the characters that lead to these cases. So we need to track this piece of information for each case. Eventually, assuming that the challenge is solvable, and that remember that the password is actually used as the decryption key, as the decryption IS key. This means that the password has to be unique, because there cannot be 2 IS keys decrypting into the same flag, right? So the password has to be unique. So after having written down all the possible cases and what are their next cases, then in the end there will be only one password that has a full length of 16 bytes. Most paths will lead to a password of 12 bytes, 15 bytes, 10 bytes. At some point there will be some dead end. So for example, remember the previous case remember or was it? Yeah. So for example, where is the jump RCX? Yeah, here. So suppose at some point we end up to case 46,369. If we end up here, we see that transitions is not updated at all, and there is actually no, and the current state is not updated nowhere. This means that, boom, this is a dead end. So if we get here, we know that the password is wrong, and it will never reach 16 bytes. So there will be only one password that leads to a full length of 16 bytes. So there are many things happening together. Let's start from somewhere. First of all, we need to track these cases. We need to know where each case starts inside this table. So let's go to the jump table. We need a way to programmatically basically extract all the cases from this jump table. Okay, I cannot scroll down that much, but you understand the idea. Basically, we need to dump all these relative offsets. Which offsets? These. Anyway, you understand all of these offsets. You can see here that the idea is pretty similar to the jump deobfuscation that we showcased earlier. This jump table is literally represented by 4-byte Lithuanian words. So this 4-byte represents this case, these 4 bytes represent this case, these 4 bytes represent this case, etc. But in this case, it's much simpler. This D word, you see the pattern? It's 860241. It's 86400241. So A158FB. A158FB. So the actual offset in the jump table is just these 4 bytes. We do not want to subtract the target from start. It's much simpler right now. It's just the offset inside the binary. So I have made a script during the contest that does exactly this thing. It's called dump cases. Guess what it does? It literally dumps all the cases. So let's analyze it step by step. I'm going to close it now. So yeah. So where did I find this information? You can search either Python switch table, switch case jump table, something like that. We want to do it programmatically, right? So yeah, I have opened this post. Potentially, there are a lot of resources that one can see. Probably this hex-raise resource is also useful. I don't see any code. Yeah, I don't see any code here. Yeah. Yeah, this specify switch heading. Okay. More specifically, this is exactly the answer I saw that helped me write my script. And the key function basically is this one: get switch info. Get switch info X is deprecated and it's replaced now by get switch info. So if we write, let us run this stuff now and see what happens. How can I clear this up anyway? Okay, so switch info. We can get that we can see that we get an object. So the jump table, you see that we pass it the base address of the jump table here. The jump table is basically determined by the jump RCX instruction. So we want to pass it the address of the jump RCX instruction. And by calling switch_info.jumps, let's print some of them, not all of them. Print j table start I. Oh, it's the start of the jump table. Okay, cool. So I did not remember that. So dot jumps leads us to the beginning of the jump table. So now we have the address of the jump table. We could just say, we could just write this, forget all of that, and we would be fine. But it's much more fun to do it that way because you learn the API as well. So let's move on. We define the number of cases. It's 90,000. This is the size of the jump table basically. And this is where we will store the final offsets of the case, of each case. So we run a loop iterating through each case, and we start from the base address and have an offset that increases each time. We basically have a counter that increases by 4. So first time is 4, is 0, then it's 4, then 8, 8. So first time it starts from here and reads 4 bytes along and converts to little endian integer. We convert to a little endian integer like that. So we read 4 bytes ahead and convert to little endian. And we store this value plus the image base. So basically we store this value, right? And these values, all these values, along with the image base. We want the image base as well. Not necessarily, but I just did it like this. So by running this script now, of course I will not run it. I already have the answers. You would end up with something like this. So suppose we want to visit a random case. Let's say this one. So printing this out, this would be case 2917, and this one would be 2918, etc., etc. Okay, okay, okay. So this is how it works. Now we have all the cases. Now what? Somehow, let me check. Yeah, we want the jump stable start again. What was that? Indirect jump. Okay. Okay, now what do we have to do? We have to parse and process each block of each case independently. So for example, starting with this block, we need to iterate over each instruction in this block the same way as we did with the jump deobfuscator. So we need to run over this block, and somehow we need to keep track of the current case. So this is case 41,257. So we need to keep track of this, and we need to store some kind of information like that. So we are at this current case, and we want to know what are the potential cases that we can, what are the next potential cases. So that would be this and this, and we get to this state from what for what character? From X. So we need to store this type of information. So we get to this state with X. What is the state? So, and we get to the next one with that um, character E. Okay. All right. So let's visualize this a bit. Okay, but we must have a plan. Like, okay, we can do this, but why do we want this information? Usually, having solved competitive programming problems in the past, this kind of problem reminds us of a tree. Like, it usually comes naturally to represent this kind of problems as a tree. Even a binary tree, a trinary tree, it means two branches, three branches, or whatever. This is the natural way to represent this type of information. So, for example, we start with J, U. Okay, these are not the same size. Sorry for that, but never mind. Um, yeah, let's increase the size. Probably write some text inside. Yeah, let's increase it a bit. 18. No, this looks fine. Yeah, this is U. This is I. Oops. Okay. So this is case. This is state 0. You see that there are 3 potential routes. From this route, we get, from case 1, we have 2 different routes, 4 and 5, right? So, um, yeah. So, yeah. Yeah, sorry about that. I could use draw.io or something, but never mind. Okay. So, J, so this is the next state. This is state 1. So, this leads to the characters L and Q, right? What about U? What about the case 2? What what are the numbers that the cases that what are the next cases after case 2? The next potential cases. So let's go to the jump table. It takes some time to load. So it's 0, 1, 2. Second case. Okay, it has only one path. This path is Y. Right? So that's Y. No. Okay, so that's Y. Okay, that's Y. I don't know why I didn't use textbooks here. Lul. Let me erase it a bit quick. If we have to do it, we have to do it right. No dirty jobs. So, okay. What's the characters here again? In case 1, L and Q. So we end up with L and we end up with Q. Okay, and from case 3, I, respectively, what would be that? So 0, 1, 2, 3. This is case 3. We end up to P and Z. So that would be, yeah, my tree literally sucks. It's awful. But anyway, you understand the logic. So that would be P, and that would be Z. right? Now, and so on and so forth. This is case 2. Um, sorry. Oh, sorry. This is not the state. This is the position. This is for the first character. This is position 0. So the first character is here. In the second, for the second character, there are these cases. For the third character, there are these cases. So this is case 2. This is state 2. State, yeah. How can I represent it now? Yeah, from case 2, we go to, let me see, from the 1 to, from case 2, we go to state 6. So we go to state 6, and this there is the character. What's the character? What's the character at case 6? 0, 1, 2, 3, 4, 5, 6. So in case 6, it's C. It's just C. Okay? And so on and so forth. So you see where it goes? The tree continues all the way up to case, up to position 15, where there will be only one byte, say B for byte. So there will be only one path leading to this last character. All the other paths will have a dead end earlier. So only one password will have exactly length 16. So what's the logic behind that? We need to somehow traverse all the possible paths of this tree. So start from J, then go up to L, then visit all the leaves starting from L. So go down from this, and somewhere here, for example, there will be a dead end. So we discard the entire branch and move to the other branch. So we move from J to Q. We go somewhere here, but somewhere here it stops. So we discard the entire thing, and so on and so forth. In the end, there will be only one path leading to, for example, starting from here, there will be only one path that will have a length of 16. So this is basically a problem of traversing a tree. To traverse a tree like that, we can represent it as a graph, where basically, okay, we will get into that a bit later. Give me a moment. How can yeah, in the way I have represented it here, it's the opposite. So in my case, I have 1, 2, 3 here. So it's 1, 2, 3, and from 1 we go to 4 and 5, right? From 2 we go to 6, as we said, and from 3 we go to, what are these? I don't know. Wait. 0, 1, 2, 3. From 3 we go to 7 and 8. It's pretty standard. So 7 and 8. This is not an 8. This is an 8 somehow. So this is basically how this graph is represented, and each of these nodes has a character associated. So basically, the edge, this is the node of the graph, and this is the edge. The edge, you can visualize it like that. There is, let me erase this. So basically, there is the letter J. So if we want to translate it in English, we can basically convert this graph to physical language. So we go from state 1 to 4 with letter J. We go from state 1 to 5 with letter Q. So there is Q. No, this is not very beautiful. Let's erase it. So yeah, we go from 1 to 5 with Q. We go from 2 to 6 with Y, and so on and so forth. We go to 3, from 3 to 7 with P, and from 3 to 8 with Z. This is how the graph is represented. So eventually, we end up with a 16-byte password, right? So yeah, now we have to somehow parse each block and extract all this useful information. Okay, so back to IDA. So of course, as always, I have already written a script that creates this graph, but I will analyze it with full details here. So let's go. Okay, let's close some stuff because, yeah, my PC is old. I don't want to tire it. Okay, so what's the logic? What's the high level logic approach? We read, as we said, we process the block by reading it instruction by instruction, and we want two things: the bytes compared here at these compare instructions, and the next state. Only these two things. So we care about the compare instructions, but only the compare instructions that have a second operand, that have a single byte as the second operand. For example, this is a compare instruction as well, but the second operand is not a single byte, it's a D word. So we want only the compare instructions that have a single byte as the second operand. And in the case of the next state, so suppose we found this byte, right? Suppose we found P. There is this common pattern everywhere that after each comparison with a single byte, there is a jump 0 that jumps to the corresponding branch that updates the current state. So from P, so we get the jump address, which is that. So we jump here and we start parsing this block until jump is found. At the jump instructions, we stop. Here we found the jump instruction, so we go to the next state. Same with here. We found the jump instruction, so we come back, so we return to the main block. So in this block, in this sub block, we look for move instructions that have the second argument as a D word now, because the second argument can be up to 90,000. And you can see from the opcodes that this is how the move instruction that we care about looks like. And the second argument, you can see that it's a D word. So in the case of this comparison, The second argument is just a single byte. Can you see that? In the case of this move, the second argument is an entire D word. So this is pretty much a pattern matching algorithm. Yeah, there are some edge cases that we will discuss though. Let's go. So we first read all the cases, okay? All 90,000 cases. So three, all these, we need all these offsets so we can read from there. And question is, um, how are we going to convert these raw bytes? Because we will read eventually we will read raw bytes from memory, from the binary. How are we how are we going to convert these raw bytes to instructions? So here is how a disassembler here is where a disassembler is important. We can either use IDA's disassembler and do everything with IDA, but I thought that this would be relatively slow, and I thought that it would be more efficient to use Capstone. Eventually, after talking with some people, after the end of the CTF, I learned that Capstone is Capstone is pretty slow, but I didn't know that at the time of the competition. So let's see what is Capstone exactly. Capstone is a disassembler written in Python. It's actually written in C, but um, there are some there is an API for Python language as well. So how it works, it's pretty simple. You give it you feed it some raw bytes. So for example, this, and you initialize the context. So you tell it that this is an x86 architecture and in 64-bit mode. And you just disassemble, and it knows how many bytes to read to create a valid instruction. So for example, it iterates this code and it prints the current address. You give it the current address. It's a random one. You can put anything you want here. And you print the mnemonic and the operands. So Capstone basically converts this byte string to these instructions. This is the whole idea. So in our case, we start from here. We read these 2 bytes, and we use Capstone to disassemble and create the actual instruction. So, yeah, let's go here. We iterate through each case. We start from case 0, then case 1, case 2. Yeah, so as we said, we want to stop processing the block when we find a jump instruction. So we iterate all of this. When we find jump, we want to stop processing, because after jump there's pretty much nothing we are interested in. So while the current mnemonic is not a jump, get the size of the current instruction, and we get it with the IDA Python API, right? So it's the same way as before. As the jump deobfuscator script, we use the decode instruction function. So we read the size of the current instruction. Yeah, and we said that we care only about the compare instructions, but not we don't care about all of them. There are some constraints. So first, this is my way of doing this. Of course, other people can do it differently, but I thought that, okay, the compares that I care about are all 8 bytes long. So 1, 2, 3, 4, 1, 2, 3, 4, 8 bytes. And apart from that, look at this. These comparisons start with 80 BC 24. So initially, here I had this. I said that, okay, if it's 8 bytes long and it starts with this, then we're 100% in the right comparison. But it turns out that I missed a lot of um, comparisons doing it that way, because it turns out that there are a lot of comparisons that start with 87C24, not only 80BC24, and this was painful to to troubleshoot at the time of the competition. So if you see here, you see how many comparisons are there with 87C24. Good news is that in the case of 87C24, the whole instruction is 5 bytes and not 8. So with that, we know that we care only about the instructions starting with uh, either these 3 bytes or they are 8 bytes long. If they are 8 bytes long, then we know it's a 80BC24. Okay. I think we could use either that or that. So if the instruction starts with any of these 3 bytes, then this is the correct instruction. But okay, I thought this was more clean. So we found the right compare. So we get the second operand. It's a zero indexed function. So operand 0 is the first operand. We don't care about this. We just care about the target byte, which is the second operand. We take it, we make sure it's an ASCII, and we convert it to a character. So we basically take 50, 0x50, and make it P. Okay, so we stored the character. Then we want to extract the state that this character leads to, the next case that this character leads to. So we have this function, next state. We will analyze it in a bit, but first see that if a new state is found, if this character leads to a valid new state, then the graph is updated. And how is updated? It's updated in this form. So it basically stores as a key the current case and appends these two pieces of information, the next state and the character that leads to that state, eventually creating a graph, but in the form of a Python dictionary. Hopefully this is understandable. Let me know in the comments if further explanation is needed for this one. But I think I'm pretty detailed. Like, I might be annoying for some people because they already know it, but the purpose is that I want everyone to understand the entire logic behind, because this is not some black magic happening. Yeah, so let's move to the get new next state. This is where this is a larger function, of course. So what's the logic? We go to the jump 0. Okay, we go to this address. So we get the jump address, which means that we get this, right? And we process the entire block. So we process this entire block. While jump is not found, means that when we found jump, it means that we have to stop processing and return back to the main block. So while a jump is not found, yeah, give me a moment. Okay, we get the size of this instruction and the raw bytes. Okay, so basically, I don't know why didn't I use capstone for this one. Anyway, we get the size, which should be 3, 4, 5, 6, 7, 8 plus 4, 12 bytes. and we get the raw bytes, which are these basically. We get the raw bytes. And we make sure that it starts with these 8 bytes. So you can see that 487, 8424, that 38D0500. So this is our pattern. This is the pattern that we look for. If we find this pattern, it means that this is a move instruction that we care about. So in that case, we take the last 4 bytes of the instruction and convert from to a little endian integer, right? And we get this as the new state and return, right? Right. So what's this? Um, Initially, I didn't have these two lines, but after a lot of troubleshooting and after some painful troubleshooting, I figured out that if I don't put this check, then there were some cases that um, some states lead. How can I explain? Some states might lead to a next state, but actually in that block, the transition is not increased. So apart from setting a new state, don't forget that we also want the transition to be increased because this is our final comparison. The final comparison that must pass is the position must be 16 and the transition must be 16. So in order for the transition to end up being 16, it means that it needs to increase by 1 for each character. So we force it like this to have an increment inside this block. So yeah, like that we create the graph, which you can see here. Sorry, graph. The graph is here. Yeah, the graph. So let's open this up, and this is how it looks like. So as we said, from case 0 we go to case 2, 3 and 1 with these letters respectively. We can verify this. From case 1 we go to 4 and 5 as we see here, and then from 2 we go to 6 and 7 or 8, right? For example, from case 98 we go to case 201, 202, and from case 202 we go to 403. From case 403, where is it? We go to 401, 801. Sorry, it's a bit late, so I'm tired. And from 8 to 01 we go to suppose this, assume this. Yeah. From here we go to 3100. Where is it? This is so annoying. Okay, 6187 and like that. What happened? Okay. So from there we go to this, for example. Nope. Okay. From this we go to 24,639. I'm following a random path, so you can see that eventually we will end up to a dead end. Unless we found the correct password, but this is unlikely. So from here we go to, for example, 49,321. Sorry, like that, and this one result. And as you see, for 49,003 to 1. And actually, all these numbers, you can see that almost the half of these are empty. More specifically, there are a lot of dead ends. And this is why the problem is solvable. Otherwise, the tree is huge. Yeah, you can see that actually for almost the half, actually exactly the half, what the fuck, almost the half of the cases lead to a dead end. So this makes the tree much smaller. If more cases led to valid cases, then the tree would be much larger and the solution would take a lot of time to be computed. Okay. So, yeah. So what's left is to figure out a traversal algorithm and try all attempts to reach to the bottom of the tree and having a full length password. So how can we traverse this tree? There are multiple different ways. For starters, there are a couple of algorithms. There is the backtracking, there is the greedy algorithm. No, there is the backtracking, breadth first search algorithm, and depth first search. Let me check. Tree traversal, breadth first search. Yeah. So these are called DFS and BFS respectively. DFS for depth first search and BFS for breadth first search. So the difference is how the traversal is happening. In the case of the BFS, you can think of the traversal happening horizontally. So starting from the source node, it goes up to 1 and moves horizontally, visits all the nodes in the horizontal line, then moves to the next layer and visits all the nodes in this horizontal line. DFS instead tries starts from 0 and moves all the way down to the leaf, to the first leaf that it meets. The first leaf that it finds, it returns back to the previous node and visit the next. Then there are no more children of 1, so it returns to 1, and there are no more children, so it returns to 0. Then goes to 2, 6, returns back, 3, 7, returns back. So this is the order of the nodes, of the visited nodes, right? So as you can see here, we want to reach to the bottom of the tree. Our purpose is to get deep down into this tree until we found a full length password. So I think in our case, fuck, I didn't see that. So I consider that in our case, DFS is will be more efficient and it's better suited for our problem. So DFS is pretty simple actually. Let me check this out. Okay, what are these? Nothing. Never mind. Okay. So let's go. There will be some spoilers here. Fuck. We don't care about this. So this is basically the entire algorithm. Let's see. Let's analyze it step by step. So, okay. Forget about this for a while. I will analyze it later. So we start from the source node, which is case 0 basically, right? Yeah. Um, yeah, I didn't write it, but there is case 0 here. Has these 3 children. From case 0, we go to case 1, case 2, case 3, right? So we start from case 0. And the base case, the case that we need to specify that determines whether we found the actual password or not. So the condition that determines whether there is whether we found a valid path is that the length of password must be 16. This is our target. This is our goal um, after traversing this graph. This is our goal, to have a password of length 16. So now, if the password is not 16, initially it is empty, right? So we iterate through um, the nodes, the children of each node. So starting from 0, we iterate um, 1, 2, and 3. We start from 1, and we see that this is where DFS happens. Yes, you might be saying now that, okay, you are iterating horizontally, 1, 2, 3. Yes, but when we reach 1, we call the same function recursively again. So basically, we reach 1 and we call the same function again. But now, the source node is 1. So in the next call of the function, the children of 1 will be considered, 4 and 5. So from the 2 children, we will choose 4, etc., etc. Right? I think I might be doing something wrong here. Shit. Yep. Yeah. I fucked up. Yeah. Sorry. J goes here. Fuck, sorry. U goes here. And I goes here. And here is L. And from 1 we go to 4 from L and to 5 from Q. Okay, so so from 0 it visits 1, and now the password has the letter J. Then from 1 we go to 4, and then the password has the letters J and L. So eventually having the entire password builds up until a 16 password is found. If a dead end is found, you can see that it returns nothing. So suppose that traverse is called recursively. It's called recursively 1, 2, 3, 4, 5, 6, 7, 13 times, for example. At this point, it stops. So it returns here. There are no more children, so it returns, and it returns from that point. So it basically moves to the next iteration, eventually going back one step. So from this node, we don't know what node was here. This node led to a dead end. So it tries the next child, and so on and so forth. Maybe it's a dead end as well, most probably, since half of the half of the since half of the cases lead to a dead end. It's most likely this is a dead end as well, but you never know. Anyway, let's exit here, and yeah, let's basically run this code. Yeah, we need to reload the graph, of course, that we created, and by running solve.py, we end up with a password. When I saw that this algorithm worked out of the blue. Like, I think I just wrote it and I was like, okay, I have to debug it now. There will be mistakes, and it just printed the password. And I did not believe that it worked uh, from the first time without having to troubleshoot anything. Anyway, it was so satisfying. I enjoyed that. So now we have the full password. Um, we can go ahead and basically run the binary again. Yep. Cmd dfsm.exe. Let's make sure that the ads are empty. Oh yeah, it threw an error. If you saw, we need to rename back to exe because we renamed the binary now. So let's run this. Very cool. And let's provide the password. We will let it run for a while and we get the flag. Finite state machines are fun. Yeah, it turns out that this entire logic that the state determines the next state and the state determines the next state, and this on this switch case thing that depends on the current state, this is basically called a state machine. Okay, so of course we're not solving the challenge like that is not enough. We need to solve it statically. So let's go to the decrypt flag method. Oh shit. What was it? Decrypt. Um, yeah, fuck this shit. Yeah, decrypt and print flag. We get here and yeah, as we said, this is AS. So basically, okay. Before moving to that part, to the AS part, let's explain what this is. This is a valid way to create passwords, to create valid passwords of length 15 and less than 16. Right? So yeah. I did it initially for testing purposes to check if it works for passwords with a smaller length of length 15 or less. Eventually, I did not need it at all. But anyway, it's still here. So I hard code the password and I calculate the key like that. Let me put these statements to the top. So I calculate the password, I hard code the password, sorry, and I calculate the key as the SHA-256 hash of this password, right? Now we have to extract the encrypted data. Yeah, we can do it like that. So we can go here and basically do some Notepad++ magic like that. Yeah, it's pretty painful actually. Ugh. Because yeah, I think you see why this I don't like these question marks, these semicolons. Anyway, let's delete 8, the letter 8. Yeah, replace all. Then we don't want, let's do some regex magic. We don't want white space, colon, white space, quote, basically anything inside, and quote. Yeah. Slash W. Not work. Why? Why nice? No. Nice. Why not? It's not like the backslashes. Oh yeah. Yeah, we basically want to ignore everything inside. Yeah, so oh no. Yeah, we want that and comma. Seriously? Anyway, okay, slash W. We want this shit to delete this shit. Basically, boom. And now we want, okay, we can do the rest manually. Not a lot. It's pretty cool. Oh, it was fast. Okay. So this is basically the encrypted data. As you can see, the 0x's are 63 in total. Okay, we're missing one. What happened? Why 63? This should be 64. Because this is AES. We need to have a multiple of 16. The encrypted data are usually multiple of 16. Is it missing somewhere? Oh, here. Yeah. So this is 16 bytes long, 64 bytes long, sorry. Yeah, we have already extracted this here. So we assert this is a multiple of 16. And after some troubleshooting and some static analysis, we figured out that the first 16 bytes of this encrypt of this data are the initialization vector of AES, the IV, and the rest are the actual encrypted data. So if we go ahead and run this now, we see that we get the flag statically. So that was a challenge, pretty much. Hope you enjoyed it. Hope you learned something new, some new technique. I don't think I forgot something. I forget actually something. Yeah, all these files that I used, all the scripts I created, not these files, only the scripts that I created, will be on my GitHub repository. You can find it here. This is the folder for challenge 5. And yeah, I have uploaded everything. And this is pretty much it. Yeah. Yeah. And this is the graph. So this is all for challenge 5. And see you on the next video for challenge 6. It was that was a pretty interesting one. I really liked that. So yeah, see you on the next. Bye.